Welcome you all once again in this course of metric spaces, and today we will discuss the complete metric spaces. Now the question is, what are complete metric spaces? So the complete metric spaces are that every Cauchy sequence is convergent. If every Cauchy sequence is convergent in a metric space, then the space is called complete metric space. Okay, so before going to define the completeness of a metric space, let us see what is the meaning of convergent sequence and why do we study the convergent of a sequence. So first, you have already studied in the course of reanalysis, if you have a sequence of real numbers, and then you can say that the sequence is convergent if for every epsilon positive there exists a positive integer n such that the mod of xn minus x is less than epsilon for all n is greater than capital N, and this x is called a limit point of the sequence. Okay, so that was the definition which you have studied in the course of reanalysis. So before going to give the definition of the convergence sequence in a metric space, let us see first we will discuss the definition of a sequence. Okay, so before going to see the definition of the sequence, let me see here is I have the photograph of Cauchy. So the Cauchy was the first person who gave the Cauchy criteria. You have already studied the Cauchy criteria in your reanalysis course. That is to say that a sequence of real numbers is convergent if and only if it satisfies the Cauchy criteria. Okay, so Cauchy was the French mathematician, and not only mathematician, he was the engineer, he was the physicist, mathematician, and he has a very good pioneer contribution to several branches of mathematics, including mathematical analysis and quantum mechanics. Now in this chapter we shall discuss the concept of metric spaces, concept of convergent sequences, and we will see that the convergent sequences, the concept of convergent sequences plays an important role to investigate the closeness of a set and continuity of a function and several other properties. So in this chapter we will introduce the convergence of a sequence in a metric space, and we will include some of the properties, and we will see what would be the Cauchy criteria in the setting of metric spaces. Besides this, we will see some necessary and sufficient condition for the convergence of a sequence, and we will see some Cauchy criteria, and then we will see some other properties, and one is a very important result, that is called Cantor intersection theorem. So we will also discuss the Cantor intersection theorem, and we will see that if you have a Cauchy sequence which is not convergent, okay, can we make it convergent? So all these things we will see in this chapter. So before going to in the detail, let us see here is what is the meaning of a sequence and why do we study the sequence, the convergent of the sequence. So here is I would like to mention that suppose you have a sequence. Sequence is what? Sequence is a mapping is a function from the set of integers to R. That is, sequence is a mapping from set of integers to R. Then for each one, so you will get S1, or you can write S1, and for 2 we get S of 2, and we write this is your X1 and this is your X2 and continue in this way. So then we get the sequence, and the nth term of the sequences is denoted by this one. So for with respect to n we get Sn, and which is equal to Xn. So this is the nth term of the sequence S. And look here it says, and then we will discuss. So now what will happen if we replace this, because these are the x1, x2, xn are the real numbers. So what will happen if we consider, so we can say that xn we denote usually like this, xn is a sequence of real numbers. So this is a sequence of real numbers. Now how we can define a sequence of elements in a set? To define the sequence in a set, we have to replace this R by your any set. Then x1, x2, xn are the element of the set, and here we need to replace it by x. So this now is a sequence of elements of the set x. Now first, the second thing is that we can define the subsequence. Subsequence means if you have xn, xn is a sequence, suppose xn is a sequence, and nk be a sequence of positive integers such that n1 is less than n2 and so on. Keep in mind this n is the same as this one. Okay, so corresponding to this n we are taking n1, n2 and so on. Then the sequence xnk is called the subsequence of the sequence xn. Okay, so that is the definition of the sequence. The second thing is that if you have a sequence xn in the set x, okay, so keep in mind now I am taking the sequence in the set x, then there exists a positive integer n such that xn is equal to x. That is to say, after a finite number of terms. So for example, you have the terms of the sequence are x1, x2, and then you have xn, and after that this positive number n, all the terms are x, x, x and so on. So this kind of the sequence is called habitually constant sequence, and a sequence where all the terms are constant, c, 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 c and so on. This is called a constant sequence. So it is very obvious that a constant sequence is a special case of an habitually constant sequence. Now the question is, suppose you have a sequence of real numbers, okay, then why do we study the convergence? Or if you have a sequence of elements of a set, okay, so why we do study the convergent of the sequence? Actually what is happening, if you will look any programming, okay, so what do we do? You develop an algorithm. So in the algorithm you develop, for example, an iterative algorithm. So for the iterative algorithm you start from a point x1, okay, you try to from any point, or you can take x naught. So you start from any initial point x naught, and then by using some kind of mechanism, with that mechanism you get from this point, you get a point x1, and then you apply the same mechanism on this point x1, you will get x2, and then apply the same mechanism, you get x3, and continue in this way, we get xn and continue. Okay, so the question is that how long we can continue this thing, because we want to find out the solution. So we are developing this algorithm to find the solution of the problem. So what we do, we say that suppose x is the solution of the problem. Then what we do, we start from there and we take say for example xn minus x. That is to say the difference between xn What is n? We will see later. So the difference between xn and x is very, very small, and now it is depending on you how small it is. So this is epsilon is less than small. So what we do, we fix the epsilon. So we fix the epsilon, we take the epsilon, suppose we are taking epsilon is equal to 0.01. So according to this epsilon, you will see that we gave the command that if the difference between xn and xn is less than epsilon, whenever n is greater than, according to this, there exists a natural number n. Okay, so after this natural number, okay, say for example here you have xn. So after this natural number, the difference between this and x, which is we are supposing a solution of the problem, is less than epsilon. Okay, and then we say that xn converges to x. So in that case, if we are unable to find the exact solution, or it may take time, it may take maybe 1,000, million or trillion iterations. So just we go to up to a finite number of iterations or up to a certain number of iterations. What we do, we find, we can give the command that, okay, if xn minus x, the mod of xn, the difference between xn and x is less than with this one, then stop. Okay, so what we will do, we will take, then this xn would be the approximate solution of the problem. So that's why we study the convergent of the sequence. Now here is the important thing is that for each epsilon, so we can take what was the definition? So the definition of a convergent sequence in real analysis was, suppose you have a sequence xn, suppose I have a sequence xn of real numbers, okay. Then we say that the sequence xn converges to x, okay. Xn is converging to x if for every epsilon positive there exists a natural number n such that the difference between xn and x is less than epsilon whenever n is greater than or equal to n. It means what? It means that after this number, and now keep in mind this n is depending on epsilon, because if your epsilon is for example 0.01, then the xn, the difference between xn and x, you may get after n is equal to 10 or n is equal to 100 or n is equal to 200. And if epsilon is equal to your this, n may be little bigger. Okay, if n is equal to as much as your epsilon is smaller, you will have to take n is a little bigger. Okay, so it is not necessary, but sometimes we see some situation like this. So this natural number depends on epsilon. So because it is us, because we want to put the criteria to stop the iteration. So to stop the iteration, then we give the, okay, if the difference between the xn and x is less than 0.000001, then stop. Okay, so that about 0.0001 is the epsilon. So according to this epsilon, we will get a natural number. If we get, there exists a natural number n such that this is holds good. So that is the motivation to study the convergent of the sequence. Now the question is that here is we have the sequence of real numbers. Now the question is what will happen if we instead of x we take x. X is or any set. Okay, if x is or any set, then what would be the definition of a convergent sequence? As if xn is a sequence, as we have defined, the xn is a sequence of elements of x, and we say that suppose we want to introduce the concept of the convergent of the sequence of elements of a set, then we can go through the previous definition of the convergent of sequence of real numbers. So, in the convergence of for every epsilon positive, there exists a positive integer n such that the distance between x and xn and x is less than epsilon. So, this means what? This means that the distance, it was because the xn was the real number. We are considering the now how we can find the distance between xn and x. So, for that we will have to consider that this set X must be a metric space. It should have a metric on it. So, according to that metric, okay, so suppose now this is your metric. So, with respect to this metric, we can say that the sequence xn converges to x. Okay, it means what? It means that the distance between dxn and x, okay, is less than epsilon whenever n is greater than this one. So, this way we can define a convergent sequence or convergent of the sequence. But it can be defined only if the set X equipped with a metric. Okay, and you will see that with respect to different matrices, a sequence may converge, a sequence may not converge. Okay, with respect to one metric, a sequence may converge, but with respect to the other metric, the sequence may not converge. So, it also depends because here is we are taking the distance between xn and x is less than epsilon. Okay, so let us see here is before going to give the formal definition of a convergent sequence in a metric space, let us see here is we have the definition. So, what is the definition? Definition is the following. So, let XD be a metric space. Keep in mind, we cannot define the convergent of the sequence in an arbitrary set X. We can define only the convergent of the sequence in a metric space, and this you can also see that one of the motivation to study the metric on a set. So, here is XD be a metric space and Xn a sequence of elements of X, and this sequence of elements of X is said to be convergent if there is an element X in X such that for each epsilon greater than 0, there exists a positive integer n such that the distance between xn and x is less than epsilon for all n is greater than capital N. Okay, and this point x is called the limit point of the sequence xn, or we can say that a sequence in convergent to x if for every epsilon positive there exists a positive integer n such that dxn x is less than x. Okay, so this we can say that a sequence xn converges to x if for every epsilon positive there exists a positive integer n such that dxn x is less than epsilon for all n is greater than capital N, and this x is called the limit point of the sequence xn. And if a sequence which is not convergent is called divergent, as you have studied in the case of real analysis. Now, what will happen if you consider x is equal to R and D is equal to usual metric space? So, what you will get? You will get the definition of the convergent sequence in real analysis. So, you will see that all the results which are holds good in the setting of metric spaces, okay, they are also holds good in the setting of real numbers, or what you have studied in your course of reanalysis. But the converse is not true. A result may be true in the setting of R, but it is not true in the setting of general metric space. For example, as I mentioned, the Cauchy criteria holds good in R, but it is not true for general metric space. Now, let us elaborate the definition of the convergent of the sequence. So, to see the convergent of the sequence, you can see here is more precisely we say a sequence xn in a metric space X converges to a point X if you can treat this dxn x. Dxn x is what? Is a real number, because D is a metric from X cross X to R. So dxn x is a dxn x. So this is a sequence of real numbers. So if this sequence of real number converges to 0, then we can say that the xn converges to x. Now look here is what is the meaning of this one? What does it mean? Meaning is that, let me recall the definition of the open ball. So I write the definition as epsilon x. So S epsilon x is the set of all points y in X such that d y x is less than epsilon. Okay. Now you compare this one. It means what? It means here you have dxn. So if I write instead of xn, I can write it is equal to xn in x such that dxn comma x is less than epsilon. It means what? So this means from here you can see that the x must be, and the xn must be in the open ball with center at x and radius epsilon. So from the definition of the metric space, from the definition of a open ball, we can say that a sequence xn is a sequence xn in a metric space X converges to a point X if and only if for every epsilon positive there exists a positive integer n such that the xn okay lies in the open ball with center at x and radius epsilon. So it comes from here, the open ball. So xn lies in the open ball with center at x and radius epsilon for all n is greater than this capital N. So that is to say you have x1, x2, x3, xn, and then you have x capital N. Okay, and now suppose this is your x, and now I have this is the open ball with center at x and radius epsilon. So this is your epsilon. Okay, and after this capital N, all the terms of the sequence xn plus 1, xn plus 2 and so on, they all lie within this open ball with center at x and radius epsilon. Now you look here is what does it mean? Meaning is that you see, if you will look here is they are the difference of any 2 point, if you take this one and this one, must be less than 2 epsilon. Always you take this and this is less than 2 epsilon because the radius is 2, so it is always less than 2 epsilon. Okay, so if I choose epsilon is equal to half, so it is less than, so it motivates, it shows that so such kind of the sequences, if they are, we will see that the definition of the Cauchy sequence later. So if this is happening, then we say that the sequence xn converges to x. Okay, now usually we use the notation to write the convergent of the sequence in the following way, that xn converges to x, or limit xn as n tends to infinity is equal to x. So these are the ways to write the convergent of a sequence. And we will express it by saying that xn approaches x, or that xn converges to x. Now, as a remark, we can see that an eventually constant sequence means the term of the sequences after certain terms will be constant. So it is called eventually constant sequence. Or if all the terms of the sequence are same, constant, then it is called a constant sequence. So an eventually constant sequence, and hence a constant sequence, is convergent.